Okay, so now we'll cover some basic concepts. Mostly we'll talk about first law, second law, and some relations related to isentropic flow. So generally, for the introduction part of this course, we'll limit ourselves to isentropic flow, where there is no heat transfer to or from the flow. Then later we will look into irreversibilities. We'll talk about heat transfer. We'll talk about friction. But for the initial part, we'll limit to isentropic flow. So first and second law, I believe you all have been familiar. Now just we'll look at some relations again. So first law, for closed system, we can write in this way: whatever heat is supplied minus work done is equal to change in internal energy. You can write it in another way by taking delta W to the other side, but that all is fine. And for open system, this is how we represent that: heat supplied minus work done is equal to the change in internal energy. So basically, we talk about internal energy, kinetic energy, and mgz. Potential energy. This is again for, I think this is some mistake. This is again for closed system. Open system, we need to consider the flow work. Okay, for that we need to talk about H. Or if we consider flow work here, then also that is okay. Otherwise, for open system, this is the more appropriate equation. So H, this, I think you all are familiar with the terms here, right? H will, anyway, I will just repeat quickly. So H will denote your enthalpy. mv square is your kinetic energy term. mgz is potential energy term. So this group is for state 1. The same group is for state 2. So two states we are trying to equate, and then we'll consider whatever is the work done and it transfer to the particular flow or a system. Okay. So generally for this course, we'll be mostly neglecting potential energy. So if you remove these two terms, this is how this equation is going to look. Okay. And also we'll talk about, at least in the introduction part, we'll talk about flows where there is no work done and there is no heat transfer. So then we are left with this portion only. So this is your basically first law for open system for an isentropic flow with no work and heat transfer. Everyone is okay with this equation?
Yes, sir.
Okay. And here we can also define stagnation enthalpy. So let us say that I bring this system to rest isentropically or without any heat exchange. That enthalpy at that point will be called stagnation enthalpy. Okay. So which means that H0 is there and V naught square is 0. So we can say that this is equal to H0. Okay, now in adiabatic flow or isentropic flow, this is what we had in the last slide. Again, we can define this as stagnation enthalpy. Okay, which is constant for a flow, which is constant for a isentropic or adiabatic flow. Now, can anyone tell me which equation is this? If you add mgh, what equation will it become?
Bernoulli's?
Yes, correct. So Bernoulli missing the potential energy part. So this is also will be used in this equation for some of our derivations, and basically it will give you the stagnation pressure. So Bernoulli, when you say Bernoulli is constant, so the constant what they are talking about is the P naught. P naught is stagnation pressure. Okay, let us also talk about entropy. So second law, I assume that you are familiar with. Second law says that the entropy of the universe is always increasing, and there are different statements of the second law which are not very relevant for this course. So entropy is defined as this: ds equal to dq by t for a reversible process. And for a irreversible process, you can write that dq by t plus some entropy will be generated, or which is lost to the ambient environment. So in general, you can say that ds is equal to ds is greater than or equal to dq by t, or in general, for a system, entropy is always increasing. That is the basic underlying principle for the second law of thermodynamics. Now let us look at some thermodynamic relations. So PV by RT, this is what is this called? Anyone guess?
Ideal guess.
I guess that's
Equation
fine.
equation of state.
Equation of state. Okay. So this is what we will use in some of our derivations. Moving on, and we'll also talk about U and H. So du I can write in this form. Du is a function of temperature and volume. But for these processes, as we'll see in the next slide, so basically we'll talk about perfect gas. Okay, so for let us say that volume is constant and du becomes a function of temperature only. And I can write du is equal to Cv by t, Cvt dt. So this also I hope you all are clear with. So basically when I want to find delta U, I will integrate this term. Okay. Similarly for H, H is enthalpy. So I can write H as a function of pressure and temperature. But let me assume that pressure is constant, or in other words, let us say that H is only a function of temperature. So for that also I can again write dH is equal to Cp. So these are some of the basic equations. Now let us define what perfect gas is. So in this course, we'll talk about perfect gas, which is made of thermally and calorically perfect gas. So a gas is said to be thermally perfect when it follows the equation of state, what we saw on the last slide, and its internal energy U and enthalpy H are functions of temperature alone. So basically it says that U and H should not be dependent on these parameters. It should be a function of temperature alone. Okay, then you can call the gas to be thermally perfect if this is true. Secondly, if we want the gas to be calorically perfect, we need to have constant Cp and Cv. They should not change with temperature. Okay, so if you satisfy these two conditions, 1 and 2, then your gas is a perfect gas. So it is thermally as well as calorically perfect. So then we call the gas as perfect gas. So this is a general assumption that we'll take in our derivations. And this again, I hope you all know. dV is equal to, this is what we discussed last slide also. CVDT and dH is equal to CPDT. So let us look at some entropy relations. Okay. So entropy we can call, anyway this we have discussed. dQ by T is the entropy. Now we can also write using the first law that TdS is equal to du plus PdV. So basically I am combining first and second laws here. Okay, so this is a consequence of both the first and second law that I can write this equation. Now I can also write, instead of U, I can write dH and then minus dV will come. If you expand, then you will say that this is fine. Now dH is CPDT, du, okay. dH is CPDT and hence I can write ds in terms of this. So if you take this t to the RHS, it will go in the denominator. dH will be Cp dt by t and minus Vdp by t. Now if I use this equation of state here, okay, it is a perfect gas, so it should also follow the equation of state. If you combine this, you can get, instead of Vdp, I can write dp rdp. Okay, so this is just elimination of this that you can try and see. Anyways, so if you integrate it, now remember we have also assumed that Cp and Cv are constant. Then we can just take it back, take it out from the integration, and we can do integrate like this. Delta S is equal to dt by t and dp by p. R is also constant. So we'll get log relation. Similarly, we know that du is equal to Cv dt, and if you integrate that du relation, then you will get this Cv log t plus R log v. Fine. So with that, we'll stop here. If you have any questions, we can discuss now.